Hello everyone, my name is Aus. Together with Stefan Gosi, we are leading the topic group Outbreaks, which is part of the focus group AI for Health by ITU and WHO. We are also part of the AI audit, and if you are also participating in one of our audits, this presentation might be interesting for you to learn more about outbreak detection. What is the objective in disease outbreak detection? So usually detecting an outbreak is rather hard from case data, for example. So usually we are talking about signal detection, and a signal is just a hint for a potential outbreak. What you are seeing here is a time series. In the x-axis you see time, in the y-axis you see the count or occurrence count of some disease, let's say Salmonella. And what you would usually do is to say a potential outbreak is occurring when we are seeing more cases than we would expect. And the number of expected cases is usually modeled via a statistical model that takes into account trend, seasonality, and other epidemiological factors. And on top of that, we usually put a probability distribution that then models the expected case counts that we are seeing given some time. And in blue, you see this expected case counts based on the data that we saw in the past. The red line is some kind of threshold, which we can also define statistically to say within which confidence interval we are allowing case numbers to occur, and if they are outside this interval, then they are quite unlikely, and then this is a hint or a signal. And the red lines that we are seeing are case counts that are exceeding the threshold. They get then a little red triangle in the bottom, and we are talking about signals right there. And in the real world, epidemiologists might look into that, send investigation teams to wherever these case counts are reported from, and try to find an underlying source, such as some dirty utensils at a butcher, or a sick child in the school and transferring some kind of influenza virus there. So these epidemiologists that are investigating cases might identify outbreaks, so one underlying cause, and then they will report that. And within the system, we can use these reported outbreaks as labels for our machine learning model. So we could apply supervised learning to that problem. To the left, you see those confirmed outbreaks. The orange triangles and lines are confirmed outbreaks. And what we then could do is to take a machine learning model, run it on past data, validate it on some present data, and see how good our algorithm is able to learn the problem of outbreak detection. So a simple train test split, and we are good to go. But the problem is here that this is not the only setting in which we have disease outbreak detection algorithms. There are also other use cases that are quite different, and that are, so benchmarking them would be not so easy. They function quite differently, and let me show you how they work. So this is some kind of other, so this is another family of disease outbreak detection algorithms that doesn't look on a single time series, but that uses temporal spatial analysis to detect outbreaks. So temporal, spatial. So the spatial aspect is the circle. We are randomly drawing circles of different sizes and positions. And the circle that we are looking at, we are comparing also with past data, let's say from 1 year ago, and do a statistical test there and see or look for significant changes in the amount of cases that we're observing. And in red, you see signals for some disease maybe, and in the gray circles you don't. But comparing these two algorithms to run a benchmark on both of them is quite hard, because the other algorithm, the time series, will have one aggregation and looking at one single time series to run or to run outbreak detection. And this one can be run on single case data and will do many kinds of aggregations. And you could compare them maybe if you take the other algorithm and also apply multiple testing, but then you would need to modify the other algorithm, and then you would also need to apply some kind of spatial aggregation that's similar to those circles, which might not be desirable because the other algorithm usually runs on spatial aggregations that are useful in a political sense. For example, you would look at time series that are aggregated over one county or one federal state, and they usually have a different shape than those circles. And the big question here is how to compare both algorithms and other algorithms. In summary, the problem that we are facing is that algorithms that are used in disease outbreak detection don't share a similar strategy. There are algorithms that run on single case data. Others require aggregated data. There are algorithms that will always look at this at one single kind of aggregation. So comparing this algorithm would only be meaningful if you would compare to an algorithm that runs on the same aggregation. There are algorithms that will look for different kind of or many aggregations at the same time and apply multiple testing to find outbreaks. And finally, and that's something that I haven't talked about yet, is that algorithms usually don't explicitly model seeing no case at all, or seeing cases that are not part of an outbreak, which we call endemic cases. But some do, and how do you take this into account into your scoring strategy? So up to now, you should know about what outbreak detection is, that there's different kinds of algorithms that are hard to compare, but comparability is important for benchmarking. And that's exactly what we were working on, and we also have a proposal that might solve this problem. And the basic idea here is that we take the labeled data, so our expert labels and our expert labels together with the epidemiological data, and from that we form some kind of cell grid. You will later see a picture of that grid, but what we are basically doing, the intuition behind it, is that for each cell we model the probability of seeing an outbreak, and then we take an algorithm that is supposed to tell us the probability of seeing the outbreak given that same cell, and then we compare both probabilities. And if you are a machine learning expert, or you are familiar with machine learning or AI, that's the typical use case to score algorithms, that you compare the true with the predicted values. So P of the I given X is simply the probability of seeing the data label, which might be an outbreak label, I given our cell X within the grid. And P hat of the I given X is the same, but as the output of the algorithm. So this is our predicted value. So we can eventually do a cell-wise comparison of the data to get a score on how good our algorithm is doing. This is also a formula. I won't go into much details, but the probability of seeing the I given X, or the ground truth, is simply the number of cases that we are seeing with data label I given X divided by the sum of all occurrences of all data labels given X. And p hat is just the probability of seeing the I given Sj and X, and Sj is the signal. So our algorithm will produce some kind of signal, which might be a probability, it might be a p-value, and this is then multiplied with p hat of Sj given X. So how likely is it to see a signal given the cell? One cell grid might look like this. This is an example that we created, which is, as you can see, two-dimensional. You can imagine x1 being some kind of time dimension, let's say epidemiological week, and x2 might be a spatial dimension, something like county. And what we are seeing here is signals. These are the colored boxes, so these are the outputs by the algorithms. These are the outbreak hints, and in black you see the ground truth data. Circles with numbers are cases that belong to outbreak 1, 2, or 3. So this is our data label, and the data label is an outbreak label, and there are 3 outbreaks named 1, 2, and 3. Then we have sporadic or endemic cases, so people got sick with the disease but are not part of an outbreak, and these are the circles with the X in them. For example, in the bottom right you see 6 such endemic cases. And then you have the circle with the single line through them, which is an empty set, and these are non-cases. So within the cell we are not observing anything. And you see 3 kinds of signals. So signal A, for example, captures all outbreak 1 cases and 1 endemic case, so it's quite good. Signal C misses to detect 2 from out of 3 outbreak cases, and B is quite unsure. It detects all the outbreak cases that are part of 3, but also a lot of non-cases. And as you see, the color of B is not as rich as the other colors, and this should indicate that the signal strength here is much lower than with A and B. And in the bottom right, you also see that A also has a component with much weaker signal strength than in the middle of the plot. And basically what we now can do is just calculate P of the I given X, so our ground truth, and P hat of the I given X based from the signals, and just do a cell-wise comparison. P hat, the I given X, could look something like that. So we run a pseudo algorithm, and the algorithm then, for example, set for the class endemic, when you're looking at the very left, that cell 0, 2, and 0, 3 are endemic with a probability of 1. And the reason for that is that we are seeing cases there. So there are people getting sick, but none of the 3 signals A, B, and C were able to associate both these cases with an outbreak. So the algorithm then simply assumed these must be endemic cases. The cell 04 has a probability of 0.4 being part of an outbreak. That the reason for that is that 1 of 3 signals was able to detect an outbreak case there, but the other two failed to do that, and voting against each other, we come up with a final probability of 0.4, and so forth. So all the signals are then used to calculate p hat of di given x, and then you can compare both, and the result is something like a confusion matrix. When you apply some kind of thresholding, then you get a confusion matrix for all the classes, but you can use all the usual metrics that we typically use in machine learning AI, which is specificity, sensitivity, F1, R2, Breyer, and so forth, because we just get a vector for the true values p di given x and p hat di given x for the predicted values. With that, we also added some kind of epidemiological weighting, because detecting an outbreak is not the same as detecting an outbreak. We much rather want to detect outbreaks that are large. We much rather want to detect them early, and we want to be spatially accurate. So it doesn't help us to detect an outbreak when it has been ongoing for 3 weeks. We don't want to say there's an outbreak somewhere in Germany. We want to know where exactly. And missing a large outbreak over a small one is also bad, and we want to avoid that. And for that, we applied some kind of weighting that you are seeing here. So brighter colors mean higher weighting, and darker colors and blue means lower weighting or zero weighting. And what you can see is that the blue dots are cases, observed outbreak cases, and around them we are drawing some kind of Gaussian distribution that gets weaker the further we are away from outbreak cases, so that when you are inaccurately detecting outbreak spatially wise, then the weighting for the signal that you create that is further outside is lower than the signal that is inside. Also, cases that are together will increase the weighting, which favors detecting large outbreaks over small outbreaks. We also applied case-based weighting only. So if you don't want to use this Gaussian approach, you can also weight cells by the amount of cases they hold. As you saw in the image before, there were cells with up to 4 cases. So that also might be sensible. And what you can also see is that somewhere between 1 and 2, you see a cut. And the reason for that is that we also don't want to detect outbreaks too early, because then our algorithm will always detect an outbreak. And for that, the weighting for detecting an outbreak that's too early is equal to 0. And the same can also be applied in more dimensions, as you can see here. It's the same example, but 3-dimensional, and you can see in the middle that the colors are yellow, so there's high weighting because there are some outbreak cases close to each other. To the left, you can see a lot of blue dots. That's because these are cells that would be too early, or detecting one of having an outbreak signals around there would mean that you would detect the outbreak too early, and that's also punished. But to the right, you see the fading colors. And with that, I would conclude that's it. If you have more questions, reach out. And otherwise, I wish you much fun running one of our audits. See you.